Good evening, everyone. Now we are at the second and final part of our day two evening session. As this evening approaches, we are delighted to welcome Professor Pankaj Agrawal, a theorist who has shaped India's quantum discourse over the decades. Currently, with CQUERE at TCG Crest, Kolkata, Professor Agarwal is known for his deep research insights into the quantum correlations, non-locality, cryptography, and communication. A PhD from University of Washington and a long tenure at the Institute of Physics, Bhubaneswar, his research brings foundational quantum science and futuristic applications with forays into high-energy physics phenomenology. He is also a mentor and an educator, helping usher in the next generation of quantum thinkers in India. We welcome you, Professor Pankaj Agrawal.
Okay. Thank you very much for this introduction. So, good evening, everyone. So, let me try to make it full screen. Okay. So I am Pankaj Agrawal, and I am at Secure TCG Crest in Kolkata. So, I am a physicist. So, my perspective on quantum computing is that of a physicist. I mean, rather than that of a computer scientist. And as you know, this is a vast subject. And one can give a whole semester course on quantum computing. And I have, I think, 1 hour 20 minutes or maybe 25 minutes to discuss this topic. So I will be very brief about many different topics, and I may not be able to get to some of the more celebrated algorithms because for that one needs many classes. Okay. So let me start with outline. So there is some brief introduction. Then, for any quantum computation, basic building blocks are quantum gates. There will be very, very brief discussion about it. Then any computation is implemented using a quantum circuit, which is made up of quantum gates. So we will again our discussion will be extremely brief there. And why quantum computing is interesting, why it may do better than classical computing. This is discussed in this topic, quantum parallelism. Okay, whether we can really gain using quantum computers. Then I will talk about some very elementary algorithms which were introduced first: Deutsch algorithm, Deutsch-Josa algorithm, and Simon's algorithm. And I will just have one slide each on these famous algorithms of Shor and Grover. Each algorithm may especially Shor algorithm will require several classes. If one really wants to do justice with it. So I will just have a statement of those problems. Okay, and so let me start with the introduction. Okay, so a computer where a computation is done following the laws of quantum mechanics is what is known as a quantum computer. I mean, so any computational task as simple as addition, multiplication, or more complicated like displaying graphics or updating or searching a database is done by a computer according to some algorithm. So if you are on a classical computer, you would like to use some classical algorithm, and any classical algorithm will be implemented by applying a sequence of logical operations on a string of bits. So this sequence of logical operations, individual operation, they are gates, classical gates like or, not, and gates, and this together, the a sequence or a particular combination of these gates will form a circuit, and this circuit will has input as a string of bits. Then we will manipulate these bits using that circuit, and then we'll make a measurement to get the output. So something analogous will happen in the case of a quantum computer. So a quantum computer performs a task by following a quantum algorithm. So a quantum algorithm is a sequence of unitary operations which are carried out on a string of qubits. So here individual unitary operations, they are usually called quantum gate. And when you put them together, and then you can make a what is known as a quantum circuit. So there, you have a sequence of logical operation on bits. Here we have a sequence of unitary operations on a string of qubits. So what differentiate a classical, computer or classical bit as compared to analog of bit, which you have in quantum mechanics called qubit, that it can exist in a superposed state. But if you have multiple qubits, they can be also in an entangled state. So a qubit is basically just a system which can exist in two different states. So it has a two-dimensional Hilbert space. And if you have multiple qubits, if they are in a superposed state, then they could also be in an entangled state. So it is this feature, in particular superposition and entanglement, which go hand in hand. They may lead to faster quantum algorithm. So how it could happen? This may happen because you can manipulate a large set of data, which you can encode in the coefficient of superposition at the same time in a single operation. Say for example, if you take one qubit, its Hilbert space is two-dimensional. So it will have two classical coefficients, two complex coefficients, and you can encode the information there. If you have n qubit, then its Hilbert space will be 2 to the power n dimensional. So it means you can encode information in 2 to the power n complex numbers. Okay, so say for example, if you have just 10 qubits, the Hilbert, space will be 1024 dimensional. So in just 10 qubits, you can store 2048 real numbers. So that much data you can manipulate in one go. But there is a catch. Catch is that as we saw in the case of classical computer, in the end you have to make a measurement to get the output. So here also, even if you could manipulate a large set of data in one go, but when you will make a measurement, then as you know, state will collapse to state will collapse to one of the eigenstates of the observable, and your output will be just one of those 2 to the power n coefficients. Okay. Okay, so beyond it, okay, so even if suppose you have a classical computer and you can solve a problem there, but it may require exponentially growing resources. So making a solution of problem untenable. That is where the quantum computer may help. Okay, so traditional example are, if problem of factorization or discrete log problems. As we have already seen, an algorithm on a quantum computer will be implemented using a quantum circuit, which is basically an array of quantum gates. So a quantum gate can act on one, two, or more qubits, right? So there are important one qubit gates are usually what are known as polygates, Hadamard gate, phase gate, T gate, and many others. In the case of 2 qubits, there are very famous gates which are control gate basically, in particular control NOT gate. And in the case of 3 qubits, we have two famous gates, Toffoli gates and Fredkin gate, which are control NOT and control swap gate. So in the case of like classical computer, there is a set of universal gates. So any circuit can be implemented by using just a limited number of gates. Something similar is true for a quantum computer. Usually a quantum circuit can be implemented using a finite set of gates. Okay, but in the end, so suppose there is a problem, there is a computational task, and you have an algorithm for it, but in the end, you have to run that algorithm on a computer. And if you have a quantum algorithm, you would like to run it on a quantum computer. Now this quantum computer will have physical qubits and a way of applying quantum gates and measurement to process and get the output. So a quantum computer will have physical qubits. You can apply certain quantum gates on those qubits, and you can make measurements on those qubits. And the architecture of that computer will determine what kind of gates you can apply and how you can make measurements. There are many hardware platforms where one can do this calculation. four major platforms. There are many others, but four major platforms are superconducting qubits, where IBM, Google in US, USTC in China, RIKEN in Japan, and IQM in Europe. They are putting their resources there. Then there's a trapped ions, which can act as qubits. IonQ and Continuum are two major companies there, both in US. Then you can use photons also. So there are two major companies, Xanadu and PsiQuantum. One in Canada, another is in US. Then people are also using neutral atoms, okay, also as qubits, and their QRI is one of the major companies. So these are there are many more companies in who are trying to build quantum computers. These are just to name a few. So, but there are some specialized platform also like D-Wave in Canada, where you can do more optimization kind of problem, not a general problem. So IBM actually kick-started quantum computing by introducing a system called Canary in 2017. The system had 5 qubits, and they made it publicly available, so anybody could run some circuit on this computer, and they came up with a platform called Qiskit, which can be used to program this computer. Their latest system is Condor, which has 1121 qubits. So one of the problem with quantum computer is that qubits are very fragile and they can decohere. It means they can lose their superposition, easily, or their entanglement easily. So, but if you need to, have this superposition or entanglement in your system, then because you can lose it very quickly, so it will lead to the loss in performance. So two of the major issues which are faced are that of noise control and the error corrections. Both are very important, in building a quantum computer, or in general in quantum communication also. So actually in that it is not the number of physical qubits which matter, but it is the number of what you call fault tolerant qubit or logical qubits that matter. So even if IBM has a 1121 qubit computer, but actually useful qubits will be very few. Okay, because you want qubits which can tolerate noise, or where you can do error corrections. And some of these systems even don't implement these error correction techniques. Okay, but now because of this realization, it is more important to have larger number of logical qubits than physical qubits. They just shift, and by companies, and now they are looking more into how to have more logical qubits. It means implementing error correcting codes. Okay, so recently, Google introduced a 105 qubit system called Willow, where they implemented quantum error corrections, and it was a very big news. But at the same time, in China, in USTC China, they also introduced a system with the same number of qubits. So as I was just saying a while ago, actually maintaining the coherence and also this gate fidelity. When you are applying a quantum gate, its operation is characterized by something called fidelity. If it is not large enough, very soon you will have lots of errors in your computation. So these are limiting factors. So sometimes it is estimated that one may need 1 million physical qubits to have a useful fault and tolerant quantum computer. Okay, but to have many qubits on a processor is hard. So often people use quantum chips with fewer qubits, and they are thinking of going in the direction of some parallel quantum computing. Now, one question one may ask, when we can have a useful quantum computer, but no one knows the answer. It will depend how fast technology may develop in future. As some of you may know that recently NVIDIA CEO, Jensen Huang estimated it may take 15 to 30 years. And immediately it led to the, problem with some of the companies which were hyping this quantum computing. Anyway, there is no consensus when we may have a useful quantum computer. But in India, unfortunately, we still have a long way to go. Of course, National Quantum Mission is trying to push, for to push in the direction of having a useful quantum computer in India, but I think it will take time. Okay, so this era, so this is more about quantum computing. Means I will talking more a bit of elementary quantum algorithms. So this started with Deutsch algorithm. Then there are many more algorithms along the same line like Deutsch-Josha, Bernstein, Vajrani, and Simon algorithm. But the crown jewel are Shor algorithm, which shows exponential speed up for factorization, and Grover's algorithm for database searches. Okay, and this Grover algorithm has quadratic speed up, which is known to be optimal. Of course, there are many more useful algorithms like quantum phase estimation, HHL algorithm, to solve a system of linear equations. There are also more specialized algorithms for quantum optimization, like VQE and QAOA. They are actually quite useful especially VQ in quantum chemistry and atomic and molecular physics, because it helps you to compute, ground state energy. Of course, apart from that, there is also area of doing Hamiltonian simulation, as was the original goal of the Feynman. Okay, all these algorithms can be implemented in principle on a quantum hardware, but because of the limitations in this hardware, we don't know when we will have useful quantum computer. Okay, so let me start by saying a few words about qubits. So as I said a while ago, a qubit can be thought of as a 2-qubit system or a state vector of a 2-state system. By the way, feel free to if you feel free to ask any questions, if you wish, anytime. Now, 2 states of a classical system can be described by classical bits 0 or 1. So such a system can be only in either of the 2 states, either it will be 0 or 1. But in the case of qubit, you can have something called superposition, and a state can be like alpha 0 plus beta 1. So okay, so if you want to describe a particular state in this 2-dimensional Hilbert space, you can choose a set of basis vectors. So this basis vectors called 0 and 1, they are usually known as computational basis states. They are the eigenstate of what is known as sigma z operator. Okay. And another very frequently used basis which we will be using, during this during our discussion, it is known as Hadamard basis. It has these states plus and minus, which are actually eigenstate of sigma x operator. And as you see, they are the superposition of 0 and 1. Okay. And if I make a measurement on this state psi, which is alpha 0 plus beta 1, I will get 0 with probability mod alpha square and 1 with mod beta square. And as I was mentioning, if you have composite system with more than 1 qubit, then this superposition will lead to entanglement. But anyway, we are not interested in pursuing this line. So okay, so now as we just talked about, a quantum computer will be made of qubits. So you have to make operation on those qubits, which are these unity operations are called quantum gates. So here I have listed some of the major operations that we will be using, today. So 4 of the major operations are identity X, Y, and Z, which are correspond to this Pauli operator sigma X, sigma Y, and sigma Z. So you remember our qubit has a 2-dimensional Hilbert space, right? So the operator that will act on it will be given by 2 by 2 matrices. Okay, so another important operation, as we will see, is called Hadamard operation, which is very important. So what is the action of these operators, say on a set of basis vectors? So let's choose 0 and 1 as our basis vectors. If I know the action of these operators on basis vector, I know their operation on any vector in the Hilbert space. So this sigma x is sometimes also called NOT gate, because it flips. It takes 0 to 1 and 1 to 0. It is just like a classical NOT gate, which will take a bit from 0 to 1 and 1 to 0. And another gate is called this sigma y or y gate, which again is which flips the bit but with some phase. And as you can see, these 0 and 1, they are the eigenstates of sigma z. 0 is eigenstate with eigenvalue 1, and 1 is the eigenstate with eigenvalue minus 1. But as I was just pointing out to you, the Hadamard gate will be one of the most important gate, because as you see here, h, when it will act on 0, it will take it to plus state, and will act on to 1, it will take it to minus state. So as you see, plus, as we saw just a while ago, plus and minus, they are superposition of 0 and 1. So whenever we need to create superposition, we will use Hadamard gate, and this is what will be done in most of these algorithms. Another, apart from Hadamard gate, another very important gate is called CNOT gate, and this will act on 2 qubits. So okay, so I will just explain in a while again. So here is actually a pictorial representation of these gates. So when you draw a circuit, so you have to have some notations for various gates. So this poly X gate, which is also called NOT gate, also called this X gate, you see that its notation, it flips 0 to 1. Then poly Z gate, okay, it just takes 0 to 0 and 1 to minus 1. But Hadamard gate, as I said, is one of the most important gate, because it creates superposition. It takes 0 to superposition of 0 and 1. And same thing about 1. State 1 goes superposition of 0 and 1. So that is to create superposition. But if you want to create entanglement, then 2 qubits have to interact. This is where CNOT gate comes into picture. CNOT means control NOT. So there is a controlled qubit and there is a target qubit. So depending on controlled qubit state of the target qubit will change. So if a state of the so if your state of one of the qubit is 0, control qubit is 0, then target qubit state will not change. Yani NOT operator will not act on it. But if the state is 1, then target state will change, a NOT gate will act on it. And these are the matrix representation of these gates. Okay, and here is the simplest quantum circuit, as simple as you could have. So this circuit has Hadamard gate and a controlled NOT gate. Okay, so Hadamard gate will create superposition, and CNOT gate will create entanglement. So this is a basically representation of how to create what are known as Bell states using product state, yani product state which are not entangled. So suppose you have a 2 qubits, each of them is in a state 0. Now you want to create an entangled state, one of the Bell state. So trick is, first you have to create superposition. So you apply Hadamard on one of the qubits. It will create a state 0, 0 plus 0, 1. Then when you will apply CNOT gate on it, then 0, 1 plus 1, 1 will change. Sorry, here it is 0, 0 plus 1, 0. So 0, 0 will remain 0, 1, 0 will become 1, 1. So you will get a state which is cat 0, 0 plus cat 1, 1. And then you can normalize it. So this has created entanglement. Okay, so this is what one can remember whenever we will see, in our future slides, these 2 gates, Hadamard gate and controlled NOT gate. They will be appearing frequently. Okay, so as we just discussed earlier, if you want to make a quantum circuit, then you will have to use this array of quantum gates, and this is the simplest example which we have already seen. Okay, as we have already discussed, important 1 qubit gates, and like polygate, Hadamard, phase gate, T gate, and some of the IBM computer, they also use this square root of NOT gate. Important 2-qubit gates are basically control gates, control NOT, control Z. Also swap gate is also important. It interchanges the states of 2 qubits. And there are 3-qubit gate, which are also very important. So importance of this, but as I discussed a while ago, I mean, the concept of universal set of gates is very important. Okay, because any computing hardware cannot be optimized for arbitrary gate. Okay, it will be optimized only for certain number of gates. So it means you have to, if your algorithm requires application of one specific gate, which is not there in the hardware, then you have to come up with identity which will allow you to implement your gate in terms of the physical gates which are available to you. And it turns out, there is a set of universal gates. In particular, here I have listed some of them. In particular, this control NOT and all 1-qubit gates. They form a universal set of gates. But it is very difficult to implement all 1-qubit gates, okay, because they will be depending on a continuous set of parameters, okay. So what one tries to have finite number of gates, but in that case, it can be done only approximately. So I mean, there is a theorem which tells us that if you use control NOT, H and T gate, T is basically also called pi by 8 gate. If you use these gates, then you can approximate any unity transformation to arbitrary accuracy. Okay. Then there are actually many other sets of gate. I mean, whatever is available in market, they often will use different sets of gates. Whatever can be implemented easily on that particular hardware or that particular architecture. So here is a typical example of quantum circuit. And this is the circuit which we'll be using actually now, as you will see in all the algorithms. Okay. So for example, let's look here. What you see in their number of qubits which are coming. Then you are applying Hadamard gates on those qubits to create superposition. So remember, if I have n qubits, if I apply Hadamard on all of them, I will have superposition of 2 to the power n states. Okay, then there is some black box which basically implements some function f. Usually we don't know the inner working of this box, but here is one particular, but whatever this black box in the end has to be implemented on a computer, right? So one in the end has to have a circuit to implement that black box. Okay, so this is one example. But after you apply Hadamard and you evaluate this function f, then often you have to apply Hadamard again. And in the end, you have to make measurements. So whatever you see with dial, this is basically telling you we are making a measurement on that qubit and getting some classical output. Okay. So most of these circuits will have this kind of, this kind of view. Some qubits in the beginning, you will apply Hadamard there. Then there is some box which will be implementing some function. You will again apply some Hadamard and then apply some, then make some measurements. Okay, so now let's discuss quantum parallelism. Okay, because this is sometimes, it can be confusing. Because as I told you a while ago, although we can manipulate 2 to the power n, coefficients at the same time, but when I want to get the output and when I make a measurement, I will get just one state, So that may suggest that you cannot have a quantum parallelism because one measurement will give you just one output. You are, even if you have, manipulated 2 to the power n coefficient, but by one measurement, you are not going to get their values, right? So you will need a very large number of measurements and then, it may defeat the purpose of using a quantum computer. But as we will see, this way, I mean, there are ways where one can extract some information about the function. Okay, and so you can learn some of the properties of a function which we will be computing on the quantum computer. Okay. Okay, so as we discussed already, quantum mechanics has this feature of superposition. This feature gives rise to phenomena of quantum parallelism. It means that a quantum computer can evaluate a function for many different values of x simultaneously. Okay, so let's consider a very simple function, which a function which takes a value 0 or 1 and also outputs value 0 or 1. So a domain has value 0 and 1, also output has value 0 and 1. So basically 1 bit. Now if you want to compute this function on a quantum computer, we will need to consider a 2-qubit quantum computer at the very minimum. Now, suppose now you have 2 qubits. Now suppose one qubit is in the state x, which can be 0 or 1. Another qubit is in the state y, which can also be 0 and 1. So this is the initial state x, y, where x and y can be 0 or 1. Okay, now there exists this unitary transformation, which when will act on this state xy will give you state x, but the state of second qubit will become y. It will be adding y and fx. This is a modulo sum. Since y and fx can take value only 0 and 1, so this is a modulo 2 sum. Okay, so this is the way function will be usually implemented. Now this is a unitary transformation, and how it is advantageous to us we will see just in a while. One thing you see here, if y is 0, then when this function uf will act on x and 0, it will give you x and fx. Then your function fx will be evaluated. The quantum circuit that evaluates uf is like a black box. So these type of algorithms are also called sometimes black box algorithms. And actually most of algorithm, including you may say Shor algorithm and Grover algorithm, they are also black box algorithms. So okay, so this operator uf will help us to evaluate this function f. Okay, so basically sometimes one says you make queries to this black box to get the value of function f, and this you can do for multiple values of x. Okay, and this black box can evaluate fx for multiple values of x at the same time. And this black box is also sometimes called oracle. Okay, so here we have an example where you can see how you can compute this function, for different argument at the same time. So remember I had this state here x and y. So suppose I choose x as plus and y as 0. Then I want to apply this function uf on this state of 2 qubits, right? Now plus is, as we know, 0 plus 1. So our state is that uf will act on this state 0 0 plus 1 0. Now if you see this state function uf, if it will act on 0 0, right? So what you are going to get 0 and f0. And if it is going to act on it will act on 0 1, right? Then you will get 1 of f1. Okay. Okay, so this is what is going to happen. So what you see here these two different terms have information about both f0 and f1. Remember here input argument f can take only a 0 and 1, and both of them are being evaluated by uf at the same time. So in one operation, this black box can give you both values of f. Okay. So this is what you may see in the case of quantum parallelism in action, just in the context of 2 qubits. Okay. Now here, if you see, I wrote state plus 0, right? I wrote it because I wanted superposition, right? So you can create this plus state plus by applying Hadamard on the state 0, as we have seen earlier. That is why if you start with a string of 0 and 1, you have to apply first Hadamard to create superposition. Okay. So now let's look at, so this was the case for 2 qubits. Let's look the case for n qubits. Okay, so now we have say large number of qubits, say n qubits. All of them are in this state 0. So now I will have to apply Hadamard gate to all of these states, suppose, which is a to create the maximum possible superposition. In principle, you can apply Hadamard to only few of them. You still will have superposition. But if you want to have largest number of states in the your superposition, then you need to apply Hadamard to all of them. Then as we saw Hadamard when it acts on a state 0, it gives you a state plus. So you have a multiplication of n plus states. Then I can rewrite this as a sum. This you can think of as a shorthand notation. Each plus will give me 1 over square root of 2. So there are n of them. So I will get 1 over square root of 2 to the power n. Then I have this sum where I am labeling each state by, oh sorry, there is a misprint, x1, then it is x2, okay? Then all the way to xn, where this x1, x2, xn can take value from 0 and 1. And there are 2 to the power n such terms. So there is another shorthand which one can write, which 1 over square root 2 to the power n. But now this time x represents not one bit, 0 or 1, but it represents n bits at a time. So x, so suppose you have 3 bits, x can be say 001 or 010, 101, okay? So this is a shorthand notation because when you want to do calculation, often shorthand, notations will help you, okay? So one of the very important thing which you see here, which is very important, that you can create a superposition of exponentially many terms, which is 2 to the power n, right? But I am applying only linear number of elementary operation. So as you see, I am applying only n Hadamard operator. So I am applying a linear number of operations. But what I am getting exponentially many terms. So linear operation, but exponentially many terms. This is what helps us, in getting advantage in quantum computing. Okay, so now let's look at it a bit more. So because I want to see now if how to get this superposition, how to evaluate these effects, for all possible of argument when you have n qubits. Okay, so what I want to do? Okay, I have a function which can take as inputs an n bit input, which I am labeling as x. So for example, if it is 2 bit, then it can be 0 0 0 1 1 0 1 1. But output is only 1 bit. So f is a function which takes its domain as 0 1 to power n, but its range is just 0 and 1. Now I want to evaluate this function for all possible inputs, right, at the same time. So what do I do? So first thing what I will do, I will use this n 0 state. So when you see this notation h to power this tensor product n, it means I am taking tensor product of n Hadamard operator. Okay, so what you see in this equation, that there are n 0 states. On each of those states this Hadamard is acting, but on 0 only identity is acting, right? So as we saw just a while, just in the here, when n Hadamard act on n 0 states, what you get is 1 over square root of 2 to the power n and a sum, which we are writing just state x, where x will have n bits. Okay, so I am getting this 1 over square root of 2 to the power n, this sum uf is acting on x and 0. Now I can use the action of uf, right? Now let's go back and look at how uf is acting. So when uf acts on x and y, I get x and y, this modulo sum fx. But if y is 0, then it is just x fx, right? So this is what I am getting here. right? So uf is acting on x0, so that will become x fx. So remember, this is sum over 2 to the power n terms, because this x has n bits and each bit can have two values. So total number of such combination will be 2 to the power n, right? So I have this, so it means this fx can be evaluated for all possible input by just one evaluation of uf or one query to this black box. Okay, so this is a massive parallelism, right? That one query, and it will evaluate to the power n values, for of this fx. But as I said, it is not immediately useful. This is because to extract information about the values of the function, one has to make measurements. So in the end, I want to see, okay, it has evaluated fx, but I want to know the values. Well, then I have to make measurements. But measurement will collapse it, and I will not get. I will get only just one of those states. So I will get just one of the values. So measurement of the state would give fx for only a single value of x. So we cannot obtain 2 to the power n values in one run. So we can extract only a limited amount of information about this function f. Okay, so how then it is useful? Okay, so the way it is useful is that one can obtain some global information about the nature of the function with limited number of runs. So some global properties of the function we can obtain by limited number of runs. This and that to obtain that particular property may not be possible classically in fewer runs, and one may need to evaluate function many more times than in the quantum case. So it appears that one could have quantum advantage. Okay. So actually there are many elementary quantum algorithms, including Shor algorithms, they actually do just that. So for example, in the case of Dwesh and Dwesh-Josa algorithms, we don't want to know the value of function. We also just want to know a global property of that function. Okay, as we will see, with that global property is whether function is constant or balanced. So I'm not interested in values of the function. But if you want to do the problem classically, then you will need to evaluate values of the function. Similarly, Simon and Shor algorithm, we don't want values of the function. Actually, as you will see in those cases, we want to find only the period of suitable function. So again, I want to find just some global properties of some suitable function. So these algorithms again help, not by giving us the value of function for all inputs, but we can obtain some global property of the function using these algorithms. So this is where we get quantum advantage. Okay, I mean, feel free, to interrupt me if you wish anytime. Okay, so a while ago, so we have, described this black box, right? So your function uf, it acts on x and y, and the way it acts in that x remain x and y turn to y, fx modulo sum. Now, one of the very important thing here is which is known as phase kickback. So basically, it is possible to encode the value of the function in a phase. Okay, for that your x and y have to be very specific. In particular, your this y has to be state minus. Remember, we had this state minus, which was 1 over root 2, bracket mein state 0 minus state 1. Okay. So if I expand it, so it is 1 over root 2 uf will act on x0 minus x1. Okay. Or in particular, it will become 1 over root 2 x, x0 will become fx, and x1 will become fx1 modulo sum. Now if you remember, this fx can take value only 0 and 1. Okay. So when fx has a value 0, then this state becomes 0 minus 1, which is state minus. But if fx is 1, then in bracket we have 1 minus 0, because 1 modulo sum 1 is modulo 2 sum is 0. So it becomes 1 minus 0, which becomes minus state minus. So what you see that I can rewrite this as minus 1 ki power fx x0, where fx can take values, remember, 0 or 1. So what you see here, the information about this function fx can be coded in the phase. Okay, this is also called phase kickback. Now most of the basic algorithm can be discussed using this property. Okay, as we will see. Okay, so this is actually I'm just writing something which you can try to do as an exercise, because as you will see in our this algorithm, this Hadamard gate is important. So its action on our state is important. Okay, so suppose as we say, when h acts on 0, it gives plus state. When it acts on minus, it will give us when it acts on 1, it gives us minus state. Okay, so now remember here x, when h is acting only 1 qubit, x can be 0 or 1. So I can rewrite it as in this form. When h is acting on x, 1 over root 2 sum over y with minus 1 ki power x into y. But suppose x represents n qubits, then x is a string of n bits, then n Hadamard are acting on it, then our state will become 1 over root 2 of 2 ki power n minus 1 ki power x dot y. Remember, in this case, x is a string of n bits, y is a string of n bits. We are multiplying them bit by bit. Okay. So now let's come and discuss some of these basic algorithms. So one of the algorithm which was introduced to show the quantum advantage is known as Dwesh algorithm. It is the simplest algorithm where we can have a quantum advantage. And actually, as you will see, this algorithm actually, although simple, but it has most of the features of a typical quantum algorithm. Okay. So, okay, now there are many ways one can talk about this algorithm. One way is that one says that, okay, you have a coin. You want to find out whether it is fair or biased. If it is fair, then both sides will be different. If it is biased, then both sides will be same, identical. So to do this exercise, I can introduce a function f, which can take values 0 and 1. It will also output values 0 and 1. Now f0 and f1, you can take, they represent two sides of the coin. Now if two sides are different, then the coin is fair. It means f0 is not equal to f1. So sometimes we say that function f is balanced, because one will have value 0, other will have the value 1. But if coin is biased, okay, then both sides will be identical. It means f0 and f1, they will be same. So such a function is called constant. Okay? Because for both argument, it has the same value. Value can be either 0 or 1. So if you have a classical algorithm, then you have to evaluate this function 2 times. Okay, you have to evaluate f0 and f1 separately and see whether their values are same or they are different. If they are same, then its function is constant. If they are different, then function is balanced. Okay, but as we'll see, this Dwesh algorithm will require only one evaluation. Okay, so as we have already talked about, a quantum algorithm is just a series of unitary operations usually performed on a string of qubits. Okay, and then we'll make measurement to find the value of f if you wish. Okay, so here is a quantum circuit. Okay, so let's just have a look at it. So here my input are two qubits, okay, which are sometimes called registers also. Okay, so one of the qubit in a state 0, other qubit in a state 1. Actually, we can take both of them to in a state 0, but then I have to apply this not operator to convert one of the state to 1. Okay, so I will have a state of this two qubits, which is psi 0, which will be just product of 0 and 1. Then next I will apply Hadamard to both of them. Okay, it will convert 1 to minus state and 0 to the superposition of 0 and 1. So I will get the state psi 1. Now once I create superposition, now I will apply this function uf. Remember, this function uf takes x to x and y to y modulo sum fx. After that, I will apply Hadamard again only on the first qubit. Then I will make a measurement on that. This last box basically represents measurement. So this is a circuit for the Deutsch algorithm, and how this circuit is working, that is the next thing we will see. So what we will see, to start with, you have a state psi 0. Then to Hadamard act on it, you get a state psi 1. Then this black box acts on these two qubits, I get a state psi 2. Then I get a Hadamard, apply Hadamard, I get the state psi 3. Then I will make a measurement. Then I want to see how this will help me to determine this global property of the function. So let's see. So that was the circuit, and this is what happens. What is being done by the circuit. So remember, as we saw, starting state, one qubit is in 0, other is in 1. So psi 0 is just nothing but 0 into 1. Then what I'm doing, I'm applying to Hadamard on both qubits. It will convert 0 to plus and 1 to minus. Next, I want to apply this black box operation on psi 1. Now let's just see from this phase kickback what happens. So as you see, when UF will act on X, but important thing here is the second state is a minus state, okay? That's why we started with 1 and then applied Hadamard on it. Okay, so here so second state is minus. That's why I am getting this phase minus 1 to power fx, x and minus. Okay, so as you see here in my step, after applying black box, I get state psi 2, where I've got this phase minus 1 to power fx, x and minus. Remember, we have just two qubits, right? X is a state of 1 qubit, so it can take value either 0 and 1. So I can expand it, this sum. I will get minus 1 to power f0, 0, plus minus 1 to power f1, 1 minus. Now if you remember in this, so this is a state psi 2. Now if you see, I am applying Hadamard on the first qubit only. Okay, so now so this psi 3, as you see, I am applying Hadamard on first qubit and an identity operator on second qubit. Okay, then it will convert 0 to plus and 1 to minus. Now what happens if function is constant? Constant means f0 is equal to f1. If f0 is equal to f1, then minus 1 to power f0 and minus 1 to power f1, they will have same value. If f0 f1 is 0, it will be plus 1. If f0 f1 are 1, they will be minus 1. So accordingly, I could have a state either plus or minus 0 into minus. But now suppose f is balanced. It means either f0 is, if f0 is 0, f1 is 1. If f0 is 1, f1 is 0. So in that case, I will get plus minus 1. So as you see, these are states psi 3, a state of the two qubits after this. So psi 3 is after I have applied 2 Hadamard, black box and 1 Hadamard. Now I am making a measurement. So I will make a measurement in computational basis 0 and 1. So now as you see here, Psi 3 is plus minus 0 minus in case function is constant, and is balanced, then is plus minus 1 minus. So when I make a measurement and I get a output 0, then I know my function is constant. And if output gives me state 1, then I will say function is balanced. Okay. So by making this measurement in computational basis, I am able to determine whether this function is biased or whether this coin is biased and fair, or function is constant or balanced. Now, one thing we should remember here, we don't know the values of the function. I don't know that what is the value of f0, what is the value of f1. Without knowing these values, I have been able to determine whether these values are identical or they are different. So I am just interested in this global property of the function. And so in this simple case, while classically you will need two evaluation, but in this algorithm, quantum algorithm will require only one evaluation. Any questions? Please feel free, because I don't know the background of most of the audience, so I may be talking either very elementary things or things which may be a bit advanced. Okay, so I don't know. So feel free. Okay. Okay, so now let's come to the second algorithm. In this case, actually, your input is is a n bit string. So it's a function where your input is n bit string, but output is 1 bit string. Again, I want to determine whether this function is constant or balanced. Then what does that mean in this case? If for all input f has the same value, then we say it is constant. But we say it is balanced if for half of the input its value is 0, and for other half its value is 1. Okay. Now here, as you will see, we'll see superficial exponential speed up. You see, in this very simple algorithm, you will see a superficial exponential speed up. So if I want to determine, classically, then I will need to measure at least, one more than half of the function values. So that there are 2 to the power n functions, half is 2 to the power n divided by 2 plus 1. So it means I may have to evaluate the function 2 to the power n minus 1 plus 1 times. But as you will see, for the quantum algorithm, I will need only one evaluation. So naively it appears we have exponential speed up, right? Because classically I will need 2 to the power of the order of 2 to the power n steps or evaluations, but in the quantum case only one, right? Well, so actually that is true in the case of what are known as deterministic classical algorithms. There exists a probabilistic classical algorithm which can evaluate this function with some finite error. Actually, it turns out there exist algorithms which are probabilistic in nature. They can determine this function in n plus 1. They can determine whether function is constant or balanced by just n plus 1 evaluation with the error probability of 1 over 2 to the power n. So as n increases, error probability decreases. So as you see that in one case it is n times, other case only n plus 1 times. Okay, so here we have advantage, but not significant. Okay, but as we will see, this Simon algorithm actually has a genuine exponential speedup. So here actually I will not spend too much time here, because this is just very similar to the Dutch algorithm. So here we have the similar circuit as before, but in this case I am starting with n qubit, n plus 1 qubit. Okay. So when you see this red line and the n there, it means this line represents n qubits. Okay, which all of them are in the state 0. Then Hadamard will act on all of them. Also, this n plus 1 qubit, n plus 1th qubit is in the state 1. Hadamard will act on that also. Then this black box will act. After that, Hadamard will act on all n qubit, which is sometimes known as first register. Then I will make a measurements on those n qubits. Okay. So its circuit is same as before, except here this first line, top line, represents n qubits. So only what it does, it makes mathematics just a bit complicated. Okay. So your starting state is an product of n qubit in state 0 and n plus 1th qubit in the state 1. Then I am applying Hadamard on all of them. Then my resulting state will be superposition of x and minus. Hadamard on the 1 will give me minus, and Hadamard on n0 state will give me this sum, which we have seen earlier, right? So as we have seen, that when a Hadamard acts on the state 0, and if you see the here second expression, h acting on x will give you this sum with minus 1 to the power xy. When x is 0, it is just sum over y, right? So this is what we have here. Okay. Okay, so but here I have 2 to the power n terms. Okay. Now I apply black box. Remember, this is a structure x minus. So I will have a phase kickback, and the action of UF will be just introducing minus 1 to the power fx in the front. Now if you see again, I am applying Hadamard on the n qubits. So when I do that, then I will get, as you saw just a while ago, minus 1 to the power x dot z. Okay. So you can see my state will be 1 over 2 to the power n sum over x and z. Okay, where both take values n bit string value, and minus 1 to the power x dot z plus fx, then z and minus. Okay. So this is my state. Now I want to make a measurement, right? So here up to psi 3 I have. Now I will make a measurement on those n qubits. Now suppose I make a measurement on this n qubits, right? So first register means top n qubits. Okay. Now suppose, for the sake of argument, just 1 minute. Yeah. So just for the sake of argument, when I make a measurement, I will get this z has all values 0. Okay, so all n qubits on the state 0. This is my output after the measurement. It means then x dot z will be 0. So I will have just this. The term which will be multiplying these n zeros will be 1 over 2 to the power n, sum over minus 1 to the power fx, and this sum is over 2 to the power n times. Okay. So as you see here, at the bottom expression, x dot z is 0. Okay, and this z is all zeros. Okay. Okay. So now here, suppose function is constant. It means fx for all input is either 0 or 1. Now, okay, now suppose fx is 1. Then for all term will be minus 1, and so then I am adding minus 1 to the power n times. So sum will give me basically in the end minus 1. But suppose fx is 0, then I will get plus 1. Okay. The point being, as long as fx is constant, I will get value either plus 1 and minus 1. Now, if amplitude is plus 1 or minus 1, then probability of getting all 0 will be then 1. Okay. So it means if I am getting this state 0, amplitude for all other state is 0. Okay. So if my function is constant, it means fx takes value either 0 or 1. Then result of my measurement will be just this state 0 multiplied n times. Okay, so if my measurement output is all zeros, then I know that my function is constant. But suppose function is balanced. It means half of the time fx is 0, other half of time it is 1. Right? So in that case, it will add up to 0. So if function is balanced, then amplitude for this all zero state is 0, right? So if function is balanced, I will not get all 0, I will get only some other state, right? So what is the summary here? Summary is that if I make a measurement on first n qubits, if my measurement output is all 0, then I know function is constant, otherwise it is balanced. So here again you see we are just making one query to the box, or we are evaluating box just one time. Okay. And if I use deterministic algorithm, then actually classical algorithm, then I will need exponentially, I will do evolution exponentially more times, right? Which is of the order of 2 to the power n. So there is a naive exponential speed up, but as we have seen, more realistically, it is not exponential speed up. But place where we do have exponential speed up is the next algorithm called Simon algorithm. So actually in 1994, Simon introduced his algorithm. Actually, he wished to show that true exponential speed up is not possible. But he ended up showing the opposite. So this was the first algorithm which showed genuine exponential speed up. Okay. So actually Shor was motivated by Simon's work. Okay. So this work has a feature that Shor's algorithm required. So here I have some quotes from an interview of Shor. Some of you might have seen it on internet. Okay. So there is a very famous, conference in the field of quantum, in the field of computing, which is mostly classical computing, is known as Symposium on the Theory of Computing, STOC. Apparently, this is one of the very famous symposium in the field of computing, and anybody who publishes a paper there, it is same as a physicist publishing a paper in physical review letters or Nature. Okay, so this is a quote by Shor. So in the next STOC, means it, which was I think 1994, I happened to be on the program committee. Okay, so Shor was in the program committee, which was to determine which paper to accept and which paper to reject. And he said that Don Simon had submitted a paper on what is now known as Simon's algorithm. So Simon submitted a paper to this symposium, and one of the member of the program committee was Peter Shor. And he said that that was really a very good paper, but STOC committee rejected it. Okay. So this algorithm, which is now one of the more famous algorithm, and as we will see, the algorithm motivated Peter Shor, were not supposed to be good enough to be accepted in this symposium. So one of the argument was for not accepting it, that it is a completely theoretical model which has nothing to do with real life. And so this is a quote of, it is a quote from Peter Shor. Okay. And nobody understood this algorithm. Okay. And they thought it is just a theoretical model. I always regret not bringing it up and jumping up and down and saying we have to take this, but I did not. I should have, obviously. Okay. So Peter Shor was in a committee which rejected this paper. Okay. Anyway, we rejected it. So I started thinking about the paper. And this paper uses periodicity to find an algorithm to solve Simon's problem much faster than a classical computer could. So what he noticed, Peter Shor, that Simon's algorithm is solving a problem which involves periodicity of a function. I knew that periodicity was very important for the discrete log problem, and periodicity was used in Simon's algorithm. So I started thinking about this, and I came up with a quantum Fourier transform that I thought could be used for discrete log. And if you look at discrete log and factoring, they are similar problems. Okay, so basically he came up with a technique of using quantum Fourier transform to find the period of a very specific function to solve this factorization problem in polynomial time. Okay, so just here is that Peter Shor. So Simon's algorithm is really important for two reasons. First, it showed exponential speed up. Second, it motivated Shor to come up with an algorithm for a realistic problem. Okay, so what is Simon's problem? So okay, so here we have a function which takes n bits as input, and output can be either n bits or or m bits where m is less than n. Okay. So what is the problem? So there is a secret string s such that fx equal to fy if and only if x is equal to y or x equal to y modulo sum s. Okay. So this function had a period and you wanted to determine this period s. So idea is, the statement of the problem is there is a function f with this property and we have to find what this string s is. Now this x, y and s, okay, in the most general case they are string of n bits. Then one has to determine this string s by using this function as few times as possible. Remember here range in principle can be a subset of, it need not be n bit, okay. Okay, so here thing is, again here you don't want to know the value of the function. You only want to know this secret string s. So this function has periodicity, and this is what inspired Peter Shor to solve the factoring problem. Now the classical algorithm usually require 2 to the power n evaluations, while Simon's algorithm, as you will see, will require only order of n evaluation of f. So we have an exponential speed. So this is the first algorithm, although of academic nature, where we had exponential speedup. Okay, so as I was telling you, all circuits are very similar. All algorithms, even Shor and Grover's algorithm, they can be written as black box algorithms. Okay, so only thing is, so in each case, you will be using a set of initial qubits. You will be applying Hadamard to create superposition. You will apply some function. Then after that, sometimes things might change, okay, depending on the algorithm. Okay, like in the case of Shor, we have to have a circuit to evaluate quantum Fourier transform to get the periodicity of the function. In the case of Grover, UF is replaced by some iteration operator. Okay. Anyway, but each case things are very similar. So in this case, you have first register has n qubits, upper line, lower line also has n qubits. So as you had seen earlier, I am again applying Hadamard. Okay, but this time I'm not going to use phase kickback, so I'm not using Hadamard on the lower register or this lower set of n qubits. Then I will apply this black box. Then I will make a measurement on the second register, that is bottom n qubits, as you see from this notation. After making this measurement, I will apply Hadamard gate on the first register, which is the n qubits. Okay. Then I will make a measurement on those first set of n qubits. Okay. So as you see, first part is very similar to earlier two algorithm, but there are some changes because here we are making measurements on the second register also. Okay. Yeah, second register means this bottom line qubits. Okay. Okay, so I mean, so I mean, this is my algorithm. I mean, this is my circuit. Okay, now, of course, once you have circuit, it is operating on your states, creating some intermediate state and some final states, right? So here your initial state are just product of n qubit for the first register, same thing for the second one. Then I'm applying this Hadamard on the first set of n qubits. So I'm again getting a set of state which are very similar to what we had for the Josa case. Then I'm applying this black box. Now if you see this second set of qubits are all in a state 0. So when this function UF will act, when you will add all 0, you will just get fx. Now you should remember here, fx output is a string of n bits. X is a string of n bits and fx is also a string of n bits. Okay. So this is very similar to what we had earlier. Now what one can do, one can partition this 2 to the power n strings into two pair of strings, which is one is suppose x, other one is x modulo sum s. Now suppose I is a subset of this n bit string. Then you can write a state, so you can divide this x into two pieces, x plus x modulo sum s, and but here now some x goes over only I, okay, which is subset of this n bit. Now I will make a measurement on bottom set of qubits. It means I am measuring this fx. Okay. So now if you make a measurement on second set of qubit, then measurement outcome is say w, or which is fx, or it can be f of x modulo sum s. Then this will be my state, x plus x modulo. So as you can see here, right? So I am getting fx. So whatever its coefficient, if you properly normalize it, that will be the state of the upper set of qubits. Okay, here it is. Now, if you remember, I know I am applying Hadamard on the top set of qubits here, right? Okay. Okay, so if I do that, I will get this expression, which if you look at my earlier Hadamard operations, it will be like that. But here y is x plus s modulo sum. Now here, if you want non-zero amplitude, then it will turn out your minus 1 to the power x dot z should be same as minus 1 to the power y dot z. Okay. Now for this condition to be satisfied, one can do a bit of algebra. Remember, y is x modulo sum s. So it will give a condition that s dot z is 0. Okay. So to get non-zero amplitude, your s dot z should be 0. So for the outcome z. Okay. So I make a measurement on z. Remember, z is a string of n bits. I get a particular outcome. Then for that z, I should have s dot z equal to 0. Then s is perpendicular to z. So I get one equation which can help us determining s. So what I do, I will run this algorithm say n times. Okay. So measurement will give me some information about s. But so now suppose I run it n times, then I will get n collection of strings z1 to zn, and then you will get n this linear equation s dot z1 0 and all that. Now I can solve these equations, and then I will get this string s, which is s1, s2, sn. Now this string has been determined. Remember, I have run this circuit n times, right? So of the order of n evaluation. Then of course you will need some steps to solve this linear equation. But point being, you see exponential speed up. Okay. And as you see also that this algorithm was inspired by Peter Shaw. I mean, this algorithm inspired Peter Shaw to come up with his own algorithm. Okay, so now I will just on one slide each, I will say something about Shor and Grover. Okay. So basically what Shor algorithm was about, and because if you want to describe it, it will take 2, 3, 1.5 hour, at least 3, 2.5 hours. talks. So so now if I okay, so I'm just telling you the what it does. So okay, so there exists something called RSA crypto system, which was introduced in 1971. It is one of the most popular method to encrypt messages. Okay, but this system depended on the fact that factorization is hard. So what it means, if you are given an integer, as it becomes larger and larger, getting its prime factor becomes basically, I mean, it requires exponentially increasing resources. Okay, so there comes a time where your integer is large enough, then existing computing resources will not allow you to factor it. Okay, so some of these things are called, trapped one-way function. Okay, so because if you know the factors, you can get the number back. Okay, but if you know the number, you don't know the factors. Okay, so it is one way. But there exist two methods which can allow you to find the number using the factors. Okay. Anyway, so in 1995, Peter Shor introduced an algorithm that showed that factorization in polynomial time. This was possible because he could reduce this factorization problem to a period finding problem. So one only needs a fast algorithm for finding the period of a suitable function. If you remember, this later problem is very similar to Simon's problem. Actually, we can even state this part of the problem just like Simon's problem. So here what do we have? We have a function which takes a natural number to another natural number, and there is a secret string s such that function fx equal to fy if and only if either x equal to y or y minus x is divisible by s, or this s is this period of this function. So if you compare it with Simon's problem, this statement is very, very similar. Okay. So what Shor did, he found, so question is how to find period here. Okay. Now, in this case, actually Hadamard is a kind of quantum Fourier transform. Okay, but so what he did basically generalize Hadamard to this particular situation, and that means quantum Fourier transform then allowed him to find the period of a very suitable function. Okay, I have not written down that function. Okay. Okay, so this is only part of the algorithm which is actually quantum. All other parts are classical. Okay, so suppose you are given a number, first you have to find if it is prime or not. Then you have to take many steps. Okay, all those steps are classical, except there is a function which is called x to the power n. Okay, modulo n. You have to find period of that function. Okay. But we are not going to discuss it beyond telling you that it is just a period finding problem, just like Simon's problem, except we wanted to discuss quantum Fourier transform and how does it help you to find the period of an appropriate function. Okay, so in the case of Grover, actually what was his problem? Actually, this was to solve for searching for an item in an unsorted database. This is Shor algorithm is also a black box problem. So is Grover's algorithm. In the Grover's algorithm, again you have to find a function f, which takes n bits, n string bit as input and spits out one bit, 0 or 1. So here task is to find using fewest queries or fewest evaluation n input x such that fx equal to 1. Remember, x is a string of n bits. Okay. So which may be 2 to the power n. So you have a database with 2 to the power n entries, and you want to find one or say m number of strings. Okay. So you have 2 to the power n binary strings. Binary means that 0 and 1 each bit is either 0 or 1. And you want to find m strings there. But if m is very small compared to n, then one can show that, so you want to find when this function will evaluate to 1, right? One can show classically it takes n over m steps. And okay, you have to do that many evaluation of function. But in a Grover algorithm, you have to take only square root of that many evaluation. So actually what this algorithm does, it uses what is known as an iteration operator, sometimes called diffusion operator. Okay, so what this operator does, which I have written down here, which is basically Hadamard in n Hadamard into I, then there is a function uf0, again h Hadamard n cross I, then uf. This is sometimes called Grover iteration operator. What you do to multiply this operator multiple times to amplify the amplitude of the solution. So you remember, so you have a superposition of 2 to the power n terms, only some of them are your solution. You want to amplify the amplitude of those solutions. And this Grover operator, when it acts multiple times, it helps you to amplify the amplitude of the solution. Okay, so sometimes this algorithm is also belong to a class which is known as amplitude amplification class. Okay, so to speak. Okay. So I think that I'm going to end here. Okay. I think my 1.5 hour is also up. Yeah, hello. So I think it is over. Okay.
Thank you, sir.
If anybody wants to ask anything, that is
Yes,
also fine.
we are open for questions and discussions now.